So now what we're going to do is we are going to look at the system that we are given. And you will sometimes you have that acid, you have that base, and you add a salt to it. That is going to change the amount that you have at the beginning in your ice table. Why will that amount at the beginning is going to change? Because that salt is either going to be acidic or basic. Remember, you have those salts that could be acidic or basic. We had to look at that a little bit further. So let's say I have HC2H3O2, acetic acid, and I have the conjugate of that. I mean, that's acetate. We have the conjugate of that as a salt in sodium acetate. That salt doesn't have the H in it, so it's in solution because we are adding a salt that has a common ingredient as the acid. We had to take into consideration now because of kinetics and Le Chatelier's principle, by adding that salt is going to have an effect on that reaction that's going to push that reaction towards the left, meaning towards the production of that acid. Nothing different from what we've done so far. We just are going to modify the ice table a tiny bit. So now we have an initial situation where we have the concentration of that reactant, but we also have a common ion that relates to that reactant that we have. That is going to change that initial amount that you have at the beginning of that common ion, which is going to have an effect on the equilibrium that you are going to have. So how does that look? Let's say I have silver chloride in 0.1 molar HCl. By looking at it, you have a salt and you're adding an acid to that aqueous solution of the salt. I hope you see that by adding that salt, that is HCl, that Cl ion is common to the HgCl. So now the amount of Cl is no longer going to be 0. It is going to be preloaded, meaning that it's going to have an initial amount. And that is going to try to push the reaction towards the left. Trying to prevent that salt from dissolving. So adding this common ion doesn't want that salt to precipitate. It wants to stay as a salt. And what we are going to do is come on to a case where we can predict, will that salt precipitate or not? So we are going to build towards that. I think we have enough time to do that. So when you set up your ice table, we are going to do it like the same way we did for the salts. We are not going to look at that beginning because it's a solid. Doesn't matter that it's not going to have an effect on the equilibrium expression. The only difference now is that instead of having 0 for the concentration of the chloride, we're going to have 0.1, which is coming from the HCl that we are adding. The equilibrium at the end is going to be H for the silver and 0.1 plus H from the chlorine. We're doing before is not going to change because that KSP value at the end is still going to be small, small value. So with this problem, I wanted you to show that the initial amounts of the ions in an aqueous solution of the salt are no longer going to be zero at the beginning because I'm preloading, I'm adding a common ion to the salt. And that common ion could be common to the metal or the cation or common to the anion. It could be either one because it depends if I add an acid or I add a base to it. Okay, so let's say I have the KSP value for this reaction in here. Silver sulfide, you have silver and sulfide. And I am adding 0.0010 molar AgNO3 to that silver sulfide. By adding that other salt to it, we can see that that silver is common to the salt in aqueous solution. So the initial amount of the silver is no longer going to be zero, it's going to be 0.0010. We are going to set it up the same way we did it with the other problems. The only difference is the starting point for silver is 0.0010 instead of 0. And then at the end, it gets added to the 2S for the silver and S for the sulfide. We can ignore that 2S contribution to the silver and say that the concentration is basically 0.0010. Now, we are doing that because the KSP value is so small that adding that extra common ion is not going to have a big effect on that KSP. In this case, because I'm giving you the KSP value, I can calculate the molar solubility by solving for X. And we see that that molar solubility is going to be so small that adding a 2S to it is not going to change it much either. So these assumptions that we're making hold on true. They're okay to make. Alrighty. So the KSP is not just a math constant. It's going to help us determine if a specific solution can hold the dissolved ions or they're going to precipitate. Because if you read the maximum capacity, those ions will go in as a solid into solution if you go over that maximum amount. If you recall from what we did in Chem 1, you say, okay, is the solution dissolved, saturated, or oversaturated? If you're reaching the point where you are oversaturation, then you start getting that precipitate. Because we want to maintain equilibrium, and that's the key here. The equilibrium, you have the solid in aqueous solution dissolving into its ions and go back and forth. We don't see a solid in there. But if we start adding more of those ions, because of Le Chatelier says that we're going to push it towards the left, we want to make that solid. And that's when we start seeing the precipitation occur. Now, I'm going to omit this one because of time, because I want to make sure you understand how we determine if a solution will precipitate or not. Like we did in kinetics, we are going to calculate a Q bar. This is equilibrium as a If we calculate that Q value, if I reach the saturation point, that is when the Q equals the KSP. We are at equilibrium. I don't have a precipitate yet because I am saturated. Those ions will stay in solution. They are completely dissolved in solution. When I start reaching the supersaturated solution, the Q value is going to be higher than the KSP. That's when the precipitate forms. So when we started talking in Chem 1, okay, saturated solution, supersaturated solutions, I start seeing a solid in solution. It is because of the equilibrium situation that happens between the ions and the salt that I have present. So it's just not quite as simple as we make it to be in Chem 1. You have to remember these three situations. Because of the problems you're going to be working next week, you'll have them in your notes, so it won't be a problem. So let's look at one example really quick. I have a solution of 1.0 times 10 to the minus 4 molar magnesium nitrate, and I add NaOH to a final concentration of 2.0 times 10 to the minus 4. Will a precipitate form or not? So instead of calculating a KSP, I'm going to calculate a Q. The Q is just the same as the KSP. So we're looking in the middle of the page. The Q is the concentration of magnesium times the concentration of the OH squared. Because I'm working on aqueous solutions of a salt, I don't have to create my ice table. I'm just going to take the concentrations as given. The concentration of magnesium is 1 times 10 to the minus 4. The concentration of the OH is 2 times 10 to the minus 4. That concentration of OH is squared because of the equilibrium expression times the concentration of magnesium. The Q is going to end up being 4 times 10 to the minus 12. The KSP is 1.6 times 10 to the minus 12. The KSP value is lower than the Q value. So Q is higher than the KSP. So yes, the precipitation happens. Yes, we'll see a solid in solution. So to determine if a solid happens or not, that Q has to be greater than the KSP, and in this case, it is. Now, just going to mention one more thing and we'll be done for today. And that is that when you mix liquids, the volume of the solution changes. And because of that, the initial concentration changes as well. So if I specify the volume of the substances I am adding together, you have to take that into consideration when calculating those concentrations, because they no longer are going to be what is given to you. You're going to have to use the M1 V1 equals M2 V2 to determine what the new concentration will be, and then you can use the KSP expressions to do any determinations you have to make. And that is because that volume will have an effect in that concentration. Adding two different volumes is going to dilute the initial concentrations. And I do have a problem that I'm not going to go through together, but if you have the volume of magnesium nitrate and the volume of the sodium hydroxide, the total volume at the end is going to be 100 milliliter. Those 100 milliliters are going to um, dilute that solution, and the initial concentration of that magnesium nitrate and sodium hydroxide is going to be diluted to a new concentration, and those new diluted concentrations are the ones that you're going to use to do all your determinations. The notes have an example of this. I'm going to let you look at that your own time.